Hi again, everybody, and welcome back. We're continuing some examples on projectile motion and 2D kinematics. And this one deals with a golfer that is trying to hit a ball over a tree. So I'm going to go ahead and read the problem to you, and we'll go ahead and get started. So, chipping from the rough, a golfer sends the ball over a 3-meter high tree. So, right there, I'm going to just go ahead and key that in. That is 14 meters away. That means 14 meters in the horizontal. All right. The ball lands at the same level from which it was struck after traveling a horizontal distance of 17.8 meters. On the green, of course. All right, so here's the idea. I'm going to go ahead and just dim those for a second, and the ball is going to be hit up in the air, go over the tree, and come down and land at exactly the same level that it was struck from, all right, after traveling 17.8 meters in the x direction. Okay? All right. If the ball left the club at 54 degrees above the horizontal and landed on the green 2.24 seconds later, so that's the amount of time it took for the whole trajectory of the ball. There's two parts to this question, actually. Part A is asking, what was the initial speed of the ball? That is that red arrow, that velocity vector coming off. What is that initial velocity, initial speed? And how high was the ball when it passed over the tree? All right, so when it got to the tree, of course, our hope is that it would be higher than the 3-meter high tree. Otherwise, the golfer is going to be very sad. But how high will it be when it gets to the point where the tree is? Okay, so that's part B right there. I'll remind you of that part later on, so you don't need to remember it. But right now, we're going to just solve for what's that initial velocity of the ball. All right, because we don't know the initial velocity. All we know is the angle that it was hit from. Okay. Well, we do have some information, though, about the x direction. All right, we have that displacement in the x direction, that's 17.8 meters. And so we should be able to solve for the initial velocity in the x direction because we know the initial velocity in the x direction is the full velocity, vi, times a cosine of theta. All right, so that's what we want to find out, the initial velocity in the x direction. If we can do that, we can use trig to find out what the full vector vi is that's coming off the club. All right, so that's what we want to find out. Well, while we're at it, why don't we just write that the initial velocity in the y direction is vi sine theta. All right, that'll be helpful for us too a little bit later on. And both of those can be found if we know what vi is, but we don't know vi yet. Okay? All right, so that's what we want to find out. But let's use what we know about the x direction to see if we can solve for that initial velocity in the x direction. Because after all, the initial velocity in the x direction is that vi, that full vector, velocity vector of the ball, times the cosine of theta. All right, so if we're solving for vi, that's going to be the initial velocity in the x direction divided by the cosine of theta. So we really want to find the initial velocity in the x direction. Okay? So, what can we do to find that? Well, the velocity, the ball is going up and over for 2.24 seconds, and it's going a displacement of 17.8 meters. I think we can find that initial velocity in the x direction because we have that displacement in the x, and we have that time that's spent in the air. All right? So, the total displacement of the ball is 17.8 meters in the x direction. And that time in the x direction, of course time isn't really direction dependent, but time for it to move in the x direction is 2.24 seconds. So we should be able to find that initial velocity in the x direction. That's going to be what? Well, we know that velocity is displacement over time, right? So if we take our 17.8 meters, divide it by 2.24 seconds, that'll give us our initial velocity in the x direction. And by the way, there is no acceleration in the x direction, so that initial velocity in the x direction is going to be constant the whole trip. We know the y is going to change, but the x is going to be constant. So what is that 17.8 divided by 2.24? That comes out to 7.95 meters per second. So that's the initial velocity of the ball in the x direction. You might say the x component of the ball, of the ball's velocity. All right, well now we should be able to solve for that initial velocity, the red initial velocity of the ball coming off the club at that 54-degree angle, right? Because that's the initial velocity in the x direction divided by the cosine of 54, or cosine of theta, which we know. So let's just key that in. 7.95 divided by the cosine of 54. What does that come out to? That comes out to 13.5 meters per second. That's the actual velocity of the ball coming off of the club. All right, that's the full velocity, you might say, of the ball right there. All right, so we know that, and that's actually our final answer for part A. All right, 13.5 meters per second. We've got part A done. Great. Now we need to find out, and hopefully you'll recall part B asked, what is the height of the ball when it gets to the tree? All right, well that's what we're going to be concerning ourselves with now. When the ball gets to the point where it is over the tree, how high is the ball? All right, so how high was the ball, part B, when it passed over the tree? So this right here, when it gets to the tree, what is you might say the displacement of the ball when it's at the tree? All right, so that little subscript tree right there means the ball itself. When it gets to the point of the tree right there, what is that going to be? Again, we hope that it's going to be higher than the height of the tree. And again, that 3 meters, that right there, I just have as h, or height of the tree. That's just kind of for reference. We don't really need that to find the height of the ball at that point. And different varieties of this question might ask, well, how much higher than the tree would the ball be? But we're just hoping that it's going to be higher than 3 meters. All right, so for the golfer's sake, so that the ball actually clears the tree. All right, so what is going to be that height when the ball gets to the tree? So now the horizontal distance, those 14 meters, is going to be the important part to determining how high the ball is going to be when it gets to that point right there. All right, so we now can solve for our initial velocity in the y direction. I made that pop right there. Because we have the initial velocity coming off the club. So we do know our initial velocity in the x direction. That's 13.5 times cosine of 54. But we can also find our initial velocity in the y direction, which is 13.5 times the sine of 54. Both of these directions now we can get initial velocities. Well, we had already solved for the initial velocity in the x direction. That was 7.94. But the y direction is going to be important now because we want to find out how high up vertically it has gone. So that initial velocity in the y is going to be 10.9 meters per second. All right, now one thing to keep in mind when the ball gets to the tree is that the time it takes for the ball to get to the tree in the x direction, that's 14 meters, is going to be the exact same time it takes for the ball to get above the tree, that delta y, that is the displacement in the y direction. Right, time is the one thing that links x and y components. Okay? So we have that initial velocity in the y and the initial velocity in the x. Let's figure out how much time it takes to get to where the tree is, and then we can determine how high the ball is going to be. All right. At this point, I suggest setting up a table with x and y columns. Okay, so we know our initial velocity in the x direction is what? 7.94 meters per second. All right. We also know initial velocity in the y direction is 10.9 meters per second. Go ahead and just write them in. We know the displacement, that is the x displacement to get to the tree, is 14 meters. The tree is 14 meters away in the x direction. All right. Well, we don't know the delta y to the tree because that's what we're trying to solve. All right, so we don't know that. But we do know that in the x direction there's no acceleration, right? And we should be able to solve for the time it takes to get to the tree. We don't know it quite just yet, but the good news about solving for the time it takes for the ball to get horizontally to the tree means that it's going to be equal to the time it takes for the ball to get above the tree in the y direction. Okay, so that time is going to be very important to us. All right, so we have our displacement to the tree. and we have our displacement, sorry, in the x direction. We also want to solve for our displacement to the tree in the y direction. So both of those are going to take the same amount of time. All right, well, we know that there's a relationship between initial velocity and displacement and time. Displacement is initial velocity times time. So we can take those values in the x direction and use them to solve for the time it takes to get to the tree. How far away is the tree? It's 14 meters. What's the initial velocity in the x direction? 7.94 meters per second. Let's do some math there and find out how many seconds it takes the ball to reach that point. That's going to be 1.76 seconds. All right, so that's the amount of time it takes the ball to get to the tree in the x direction, which means it's going to be the exact same amount of time it takes the ball to get up in the air to that height above the tree that we're trying to solve for. All right, now we're getting somewhere. We have our time, which means, all right, we have our time, we have our initial velocity in the y direction. Let's write down the other things we need to know in the y direction. What else do we know in the y? Well, we know there's acceleration, right? Well, that's the acceleration of gravity. That's negative 9.81 meters per second squared. And of course, what's another thing in the y? Well, the displacement in the y, that's what we're trying to solve for, right? Delta y, that is when the ball gets to the tree, that's what we want to solve for. All right, that's our unknown. So let's get rid of all the x stuff and just focus on the y, because the x helped us to find the time, but the y stuff we can use to find that delta y when the ball gets to the tree. All right, so these are all of our knowns in the y direction, and we do have a kinematics equation that ties all these together. Look, we have initial velocity, we've got displacement, acceleration, and time. Which one of our equations deals with all four of those? Well, this one right here should look familiar to you. Displacement is initial velocity times time plus 1/2 times acceleration times time squared. And I even put our values in there. All right, initial velocity is 10.9, time is 1.76 seconds. The 1/2 I made into 0.5. Acceleration in the y, of course, is negative 9.81. And the time squared is 1.76 squared. So what happens if you do your math and you get, we key all those in? What is the height of the ball when it reaches above the tree? I get 3.99 meters. And that, my friends, is our final answer. We're going to box that, maybe bold it, because that's where the ball is going to be when it gets to the point where the tree is. So thankfully for the golfer, it's going to be higher than the tree. The tree is only 3 meters high. There's plenty of space. It's almost a meter higher than the tree. So the ball is going to clear the tree and keep moving, hopefully onto the green. So that's our example with the golfer and the tree. If you have any questions, please make sure you ask me. But in the meantime, thanks for following along, and I'll see you on the next one.